Just wait. Yeah. So good evening to all. I'm very happy to have today Dr. Abhishek from the 2012 graduate batch who has accepted the invitation to share his life's journey and how chemical engineering has eventually throw opens opportunities in almost all I would say career options or different ways by which chemical engineering can touch life. I had always believed, and I think would have told as part of my class lectures, that chemical engineering is one such fascinating discipline that if you're a chemical engineer, probably you can understand every other processes associated with life and living at large. And the title, or rather the concluding session for this 2020 cannot be much more fascinating than this title by Abhishek. And Abhishek is an extremely scholarly person. I have already shared his CV, so I'm not going to take large time, but I would just want to reiterate to the younger students that today he is as a postdoc research scholar in one of the very sought after labs that every PhD aspirant would like to enter at least once in their lifetime. So I would wish all the juniors will take this opportunity to interact with Abhishek and make the best use of the Alumni G Meet. Thanks, Abhishek, and now the stage is yours.
Uh, Thank you so much, sir. Well, it's been an honor. We have scheduled this in August, but I was engaged in other commitments that I couldn't really meet you folks earlier. But yeah, well, just to quickly iterate on what Naren sir has just mentioned. Well, I believe that Naren sir has joined Sastra in August 11, August or December 11. Just before I finished my semester, and I was about to move to NCL for the last part of my project, the final year project. Yeah, he was like my off-campus advisor, apart from Ranade sir or VBR sir, however you recognize him. So yeah, he was he was my off-campus advisor for my thesis back then, and so I think after his arrival, there was a huge shift in the approach in the department of computational modeling, and how do you move slightly away from traditional chemical engineering to an interdisciplinary style approach. You might, I mean, I have been made aware of the Scilab coursework, Aspen tutorials that you guys have been doing. So yeah, that was quite fortunate and really unfortunate for me that none of my advisors has ever taught me a course. That happened to me in master's, PhD, as well as with bachelor's, but that none of my advisors have really have mentored me, but never really taught me a course. So that was one of the greatest, I should say, bucket list that I have missed. But yeah, coming back to one of the questions that I got asked. So yeah, the way I would like to tailor this an hour or so meet is just ask me anything. It's sort of an AMA. So I've been I went through your previous presenters, what they have covered, and I don't want to repeat the same exact things. Just kind of boring and stupid. So I'll just try to make an addition to what they have said. I'll try my best. But it would be great if you guys have very specific questions to ask. Just shoot me, and I'll try to answer that. But in the meantime, I'll just go on a certain pose the questions, unmute and ask. And in the meantime, I can just go on with my talk. It's very informal, as like other talks. So feel free to ask me any questions in any language. when I say any language, Tamil, Telugu, or Hindi, I'll try to get as much. The communication should not be a barrier in this case. So, yeah. The earlier question was, how did I move from NCL to MS? Well, it was quite simple. I was doing my project at NCL, and I really wanted to do a career in grad school abroad. So I started applying for schools, gave my GRE, TOEFL, applied to a bunch of universities. And after I got into NCL, I realized that I really wanted to do or pursue my master's in CFD. It's just because of the environment that I was in. VVSR or Ranadisar's lab, the IFMG group, back then, I don't think there is any IFMG anymore because VVSR has moved on to another position. So the group was mostly doing CFD work. And the group comprised of chemical engineers and mechanical engineering students. Yeah, that really fascinated me because we all did fluid dynamics, and that was taught to me by Ponnuswamy sir. So I saw a different perspective of how the fluid dynamics that you learn from your textbooks, answer your questions in the exams, really work in a real world application from a scientific perspective. So that really fascinated me, and I started reading about it. And after a certain time, then I realized that I should be applying mostly or do pursue my master's in the field of CFD. So the one thing I did is I applied to the universities. That was a bit early, but too late to actually modify anything with respect to my application. But I started contacting professors through emails. So, and NCL was the only place back then I had internet connection. So I used to stay after 6, and because that's the morning back in here in US. So I used to stay late nights and keep writing emails to professors, contacting them if they had projects or openings in their groups for the master students. As you all know, and it still applies, that 95% of the emails get ignored, and the rest of the 4% of the emails gets you a no answer, and the 1% is the one that you get sort of yes, maybe yes, stuff like that. So yeah, that's how I got into the field. I got shifted gears from my NCL to the masters. I got a question here from Rajshri, and the question is, where do you see computational in the next decade or so? Will the computation completely replace experiments? So yeah, that was one of it's a really good question. That was one of the core ingredients of my talk. So from my bachelor's, master's, and the PhD, I've always made sure that what happens in ahead of 5 years. So prepare yourself after what happens in 5 years. So are your skills relevant after 5 years? Do you see competitive enough to position yourself after 5 years? So that was one of my questions. So back in my bachelor's, computational domain was not a big thing. And in our department, and as you all know in the curriculum, that I'm not quite sure about now, but in the span of my bachelor's 2008-12, we had a very minimal footprint of computational domain. When I say computational, you don't have to code a lot. It's about like translating your simple equations that you learn in CRE, mass balances, number of steps in a resolution column, to change that language to an algorithm. And algorithm, again, I don't mean that you write computer code. Step-by-step procedure on a piece of paper. And how do you translate that to a MATLAB or Scilab or Octave or whatever it is? So that's the minimum amount of skill that one needs to acquire, that I find it important, because I've been looking at what others were doing in terms of what NITs and IITs, and I was fortunate enough to see that some of the coursework of MIT courseware was open source on YouTube. So back in my bachelor's, with the crappy internet connection, Condé hostel, I just used to browse YouTube for these lectures, and I saw that the computational footprint was huge, and it was increasing. It was in the nascent stages, and it was quite a bit increasing. So that's where I have realized that that there is an edge, or there will be an edge after a couple of years of me pursuing my master's or doing anything, that computational domain will be hot topic over traditional experiments. And it's quite common sense that doing experiments is a huge setup, takes time, money, and effort. But computations has a lesser, how should I say, learning curve. And that's what I got when I started like graduating in my final year and started to pursue what I need to do next. So yeah, to answer your question, computational will not completely replace experiments. So after I graduated in 2012 until now, there was a period called predictive science. So even in chemical engineering, mechanical engineering, or whatever discipline, there was a field called predictive science that came in, which employs computational techniques to traditional practices to actually find something useful before you even do experiments. So instead of developing a huge equipment, doing a lot of experiments, people used to do a computational approach, find something useful, and then question themselves, will my experiments work or not? So that was the phase in the past 5 years where computational domain was really good. So, and the question is, where do you see computation in the next decade or so? I see computational will go in conjunction with experiments now. So this is the phase where computations and experiments coexist. And that happens in two phases. So one, computations will drive what sort of experiments will you perform. Okay, so so you might have thought of something, okay, let's do this and this and this in experiments. But before you will do that, computations will allow you to check whether this theory that you have proposed will even work or not in experiments. That's first. Second, once you do the experiments, you get a lot of data out of it. And the computations will come again into the picture to analyze this data. And that's how I see what is happening in the US and back in EU and other places, how people are really integrating experiments and computations. So yes, to answer your question, computations and experiments will coexist in the next decade or so. And will computation completely replace experiments? No, it would not. So yeah, that I hope that answers the question. Continuing on the topic of how what is a hodgepodge? So yeah, let me just say what my abstract of the talk is about. The title of the talk is really confusing. Hodgepodge is just a meaning of mixture of dissimilar elements. What I meant to say is chemical engineering is a mixture of very much dissimilar elements, and that is certainly not an it should not be taken as a disadvantage. So from the first year, you might have gone through engineering chemistry, engineering physics, workshop, labs, environmental science, environmental engineering, all these coursework. So as Naren sir has pointed out, that all these coursework will enable you to understand anything from any other field. That's the beauty of chemical engineering. So that's my gist of my talk. So the skills and the coursework that you learn here will be applied to any other field. And that's what I have observed, because I have been through so many career changes in my past few years after graduation in 2012, that I've realized that the fundamentals that I have learned in bachelor's really enabled me to understand, or at least give me an edge of what is happening in many other fields. So Yeah, that's the title of my talk in abstract that I would like to talk about for the few minutes or so. Um, so yeah, I just want to pause here and ask if anyone has any questions.
Maybe Abhishek, I would say that can you just give some example, because now we have your second year students also who are just into chemical engineering, and probably one subject that they know is process calculation, which is eventually the base on which everything else builds throughout the life,
That's right. Yeah.
finding conservations of everything, right? So
Yeah.
maybe you can just pick
Yeah.
any example without disclosing any proprietary information, just to say that how being a chemical engineer you applied different principles, which is otherwise not possible for another discipline person, right? And so that
Certainly.
could
Yeah.
be something like that.
Yeah.
Yeah.
Yeah. Thanks for that. I mean, as always. Uh, so, well, the important question here is, and you will get in the exams, what is the difference between unit operations and unit process? That's a classic question that you come across over and over again. Maybe in Viva sometimes, in your job interviews, wherever possible. But that's just a classic question that never gets old. So yeah, to be very basic and simplistic of how these sorry about that, how the chemical engineering principles are applied in various fields. So I believe the course of process operations or unit process that you will study in the second year or so, and the heat and mass transfers in the third year, CRE in the third year, and final year some electives. So for an example, I worked as in the field of atmospheric research for some time, for 6 months or so. And I was the only chemical engineer that they have employed in the history of history at the National Center for Atmospheric Research. So it's one of the atmospheric sciences center dedicated for non-classified work to support weather information. So I was working in a group for numerical weather predictions and data analysis, and that was a group, and I worked as a software engineer there. So the fundamental principles that all these atmospheric scientists. So I was surrounded by people who had masters or PhDs in atmospheric sciences, geophysics, geosciences. So these were the people, like they are like career scientists, and all they knew was a Navier-Stokes equation, simple fundamentals of fluid dynamics, and simple fundamentals of mixing. So these are the things that that they studied in their education, and they apply it for their career. So one such example is, even though the language differs, so the terminology differs, we as chemical engineers can easily understand when they say convection, when they use conduction, words like this, laminar flows, mixing that is happening in the clouds, or when the tornado approaches. It's just, when a tornado approaches, it's just not a wind. It will have particulates from the ground. So it'll just uproot trees and whatever it's on the ground, soil, sand. So it's a particulate mixture, and it's a fluid problem with particulate operation. So you don't see any unit process happening, but you see unit operations happening. So there are no chemical reactions involved. In other words, it's a lot of physical reactions happening, physical mixing. So all these keywords that they use to understand or they speak with their colleagues, you can really easily get that. And this is one such example that if you have pursued chemical engineering, or if you had really paid attention to your fundamentals, you don't need to memorize a huge book of Levinson or a unit operations book. The fundamentals, the very basic governing equations that you come across in your coursework, if you just remember that even after your graduation, when I say remember, not memorize, but in fact know the fundamental meaning, how you derive it from the first principles. So if that is done, you're a successful engineer on your part. And irrespective of what the field it is, you can understand the nuances. When they speak something, you can really get something out of it. Let's say if you're an electrical engineer or a process instrumentation engineering student or a mechanical engineering student, yes, you might have read some keywords or might have studied heat and mass transfer as a part of your curriculum, but you might not understand the big picture. So, I mean, at this point, you all must know that chemical engineering is in every product. I mean, I should not even quote any examples because it's a fact these days. So, yeah. And that's one of the examples. Like atmospheric sciences, the phase that I've worked for, it was completely driven by fluid dynamics. And one such moment I realized that if people from third year can recollect that there is this unit operations or lab or something like that, it's where you do ball milling experiments back in that old shed behind the old chemical engineering building.
Just Abhishek, that old chemical engineering building which you all cherished, probably had a very fond memories, is not there now. To your surprise, when you come back, sorry, you will see that all our labs are within the JVC building.
Okay.
So do you remember where Kumaresan sir used to sit?
Yes, of
the
course.
Cabin. Just below his cabin is actually the particle mechanics lab, right?
I see.
And mass transfer has already come. I think when you graduate, that was the time mass transfer equipments were bought. And if you remember, for the last 2 classes or something, I had come to show those new equipments of mass transfer. So the heat transfer has come again. If you remember Aragesan sir's lab, the library, just above that is the heat transfer lab. And the CRE lab is also in JNC, which is just above where Kumaresan sir used to sit. So that means the entire chemical engineering lab has now come to just JVC. So students don't have a greater liberty of walking from
Walking
JVC
around.
to or disappearing in the middle of coming from class to lab. That freedom is not there.
That's really painful, because you can run between to hostel, right? Even though you're not permitted to do that, you could run back to the hostel. But yeah, that takes away the freedom of running between. That's good to know. Well, our classes were moved to JNC back then, but not the laboratories. So yeah, that's good to know. I have
so,
few
but you
questions
continue.
here.
Yeah, ball milling. No, you continue with your ball milling.
Yeah. So yeah, one such example is the ball milling, where you do a particle distribution when you do the ball milling experiment, and that was exactly the case that happens in a tornado. So you get a big chunk that is being picked up by a tornado, and that is being like sheared across, and the principles that you apply, what is the dust that I get out, because tornado throws up a lot of things out. So it's this simple. That's how I connected the dots. Like the stuff that I did in the particle mechanics laboratory. Thanks for the laboratory name. So that's how I got a deja vu when people were talking about the particulates distribution and how they are shared in a tornado back then, because none of them. Because bachelor's is the only place where you can learn a huge wide of discipline, like huge range of topics. when you go to the master's and then to the PhD, your discipline narrows. And as everyone knows that's how the pyramid is. So, well, irrespective of which discipline that you go, you can always connect something to the fundamentals, and the fundamentals are the ones that drives everything. So, yeah, that's one of the examples. It's just that I'm being very careful of what I speak, because much of my work has been under NDA, classified or export control, that I should not be misspoken or misjudged. So yeah, hope that
Yeah, that's
that
perfect.
serves as an example. Okay, I'll just jump out to see to answer any questions here. This was something for your by a high performance software in an AI based startup. Okay, yeah. Experience. Much was that experience useful? Okay, so the question was high performance engineer. Me as a high performance software engineer working in AI startups. How does that relate to a chemical engineering field? Okay, this is a really important question, and one of the topics that I would like to talk about. What in the hell that AI software engineering has anything to do with the chemical engineering? And I can connect few dots here. Maybe I might not do the great justice about it. So in chemical engineering, you will go through a lot of math. I mean, maybe my math was really bad. The way it was taught, or the way I understood, it was mostly done as a practical need, not as to learn something. Back then, I was naive. Back in my bachelor's, I didn't really understand much of the math. It was mostly do this, and you get an answer. And that's how I set it up, how I passed my coursework. But after I moved out of the university and did my master's, and I worked as a software engineer in a couple of fields in atmospheric research and AI, I saw those simple equations were haunting me because I didn't have a really good understanding. So yeah, to answer your question, AI robotics and fields that are related to computer science, how does they are related to chemical engineering? So here's the answer. In your chemical engineering coursework, Dr. Naren sir, you might teach you thermodynamics. He might teach you the design of algorithms. People might have written some codes in Scilab, converting some of the equations. How do you plug numbers? How do you get the outputs? These are the fundamentals that you just need to know. That's all. And that's your stepping stone to AI robotics. Nothing more. So all these buzzwords, AI, robotics, data science, machine learning, these are merely a buzzword. And if you dig deeper enough, and if you are courageous enough, you might find that all the math that is going in, all the work that, all the code that is being written is as simple as you write something to solve something in MATLAB these days. So yes, just don't get scared by these buzzwords. Know these buzzwords. So yeah, how does the computation and chemical engineering tied up to these? They are tied up by design of algorithms. So learn how your equations. So when you're asked to design a pipe, you might get the roughness factor from somewhere by a simple expression. You plug in few numbers here and there, and then you take that and put it in another equation to get if the flow is laminar or turbulent or in between. Stuff like that. Wherever you see an equation, think about what are the inputs and what are the outputs. That's all you need to know in computations. And that's what is driving AI and robotics. So when you plot something on a graph in an Excel sheet, you have, let's say, 3 data points, and then you just connect it with a straight line. If someone asks you, what is the value of something that falls in between these 2 points, and you can you can say that if you fit a straight line and when you plug some inputs, you get the output. That is the answer. And that is AI. So, and robotics is just a piece of a machine that follows this algorithms, does mechanical. And when people talk about robotics, people say that what are the actions that it is performing? Yes, that is certainly important, and that is a field, and that is mechatronics, mechanical engineering, electrical engineering. But what that robot is being run by is sheerly algorithms and numerical methods. So computations in chemical engineering doesn't really answer how to drive a drone or create an AI algorithm for facial recognition. But if you see the code of AI robotics, you see the simple math. And if you understand how you do your simple unit operations on a piece of paper or design an algorithm, you can directly relate that to all these algorithms in AI and robotics. That's as simple as that. And that was my first job right after my PhD. Even though I had a PhD in chemical engineering with a huge focus in computations, I had no idea about AI or robotics. The firm or the startup, they just needed someone with a math background who can code, who can translate something from an equation to piece that can work. So fortunately, I was able to fill that, and that's how I made my transition to AI. And as I spent like 6 months in the startup, I just realized that I was already bored because I was already because I already knew what the ins and outs of what the AI and what the business model was, how they're doing the AI and robotics. It was quite simple for me to understand back then. So, and I just made my career transition to atmospheric sciences because after my graduation, I was in a phase that for 1 year, let me just experiment myself with doing really weird things. I thought of a career in Wall Street for some time, and I gave some interviews for investment banks because the equations that they use and the quants, the people are called as quants. When you apply for when an engineer applies for a Wall Street job or or in a financial market, people are called as quants. The job is just to plug in numbers to the equations and then start predicting it. So that was a natural fit for me. So this is how I was just playing around with the 1 year that I have set myself to experience out of my comfort zone. So I had another question here: how AI and machine learning has changed CFD you see currently, and what we have to do to keep up with the dynamic changes. Yeah, that's a really good question, and one of the hot topics right now, and one of the highly funded projects here in my workplace, Argonne National Lab at the U.S. Department of Energy. So I can talk about it in a bit good detail here. So let me just give you a quick background here because I'm running out of time here. Sir, I just want to ask if I'm allowed to go over after a few minutes.
Yeah. No issues.
Okay. I'll answer this question like AI and machine learning. So I'm pretty sure that the CFD, when you do a traditional CFD, you start with Navier-Stokes equation in 1D or 2D or 3D, depending upon your expertise or the level of complexity. My master thesis was, even though I wanted to do CFD, inspired from VVR Sir's lab, and I'm still in touch with all the folks over there. Yeah, I have established some really great networking that I have got at NCL. Few of the people who were pursuing my the MTech, because MTech at NCL was just started back then. Maybe first batch might have passed out when I went to NCL for the project. There was an MTech program, Advanced Simulation and Modeling, and that's what it was called back then, I think. I had few friends. I have made few friends over there, and they are now doing PhDs and postdoc. One of the best friend I have made is doing a postdoc at MIT these days. So all these people were doing CFD. You can't just ignore when your project is something in unit operations, heat and mass transfer, process economics. That was my topic in my bachelor's thesis. But you cannot just ignore when you attend a group meeting of VVR Sir, and people start talking about these things that you don't understand. Things that you don't understand is what keeps up the curiosity. That's just the human nature. So, and the CFD was conducted traditionally. So you have set of equations, you run some simulations, and if you change from 1D to 2D to 3D, the computational intensity increases because you have more equations to solve in a simple way, in simple terms. So even if you have the world's biggest supercomputer, and the biggest supercomputing computer is with the US DOE, it's called Summit, which is scheduled to decommission. The Summit has done its job. So it's now at Oak Ridge National Laboratory in Tennessee State. They're trying to remove it and then replace it with much bigger machine. So US is trying to be a leader in exascale computing, and CFD is one of the hottest projects that you can get your hands on one of these insanely huge supercomputers. When I say insanely huge supercomputing, it occupies the entire floor of Jiva Chaitanya, and believe me in that. And those many racks that you need to actually build that huge supercomputer, and people do use that to solve the CFD problems. So one such project is, you don't need, so the funding came for CFD is, you don't need to run all these equations again and again. So when you run a CFD simulation, you get some temperature profiles, velocity profiles, stuff like that. You get output of these simulations. When you plug that into an AI machine learning model and train it, you can get some predictions. And that way you don't have to re-simulate or perform a simulation again. It's just like fitting a straight line. So you take your data from CFD, fitting it to a straight line, and then try to and start predicting it. And that's how AI and machine learning is. So it's just not CFD. AI and machine learning is coming into every field. Well, much of my research is in molecular simulations. I wouldn't talk anything technical in this context for this audience. It's mostly materials discovery, performing simulations to discover next materials, stuff like that. I was doing some research in catalysis, water, understanding water, isotopes, battery fuel cells. These are, so even though my research or my publications, I would say, are in a molecular simulations field, the applications were very different. So I was just jumping from application to application, applying the same principles of molecular simulations and high performance computing. So to answer your question, AI and machine learning has been or is coming very gradually into every domain. So CFD, unit process operations. So it's very simple that if you're designing a reactor, there are certain parameters to optimize, right? So if you have a certain height, you fix certain things. So you fix certain height, diameter of the vessel, and then start, based on these assumptions, you start designing it. And even if I can connect the design of distillation column, the number of steps calculation for the distillation column, you set certain steps, and then you start solving the problem. But what if you cannot fix these assumptions? And that's where AI and machine learning can come into rescue, because you don't have to assume anything. You can just like fit certain things to this black box AI, and you don't need to learn AI machining from within. All you need to know is, how does it work? If I just put in some inputs, how are my outputs going to make sense? So because AI or machine learning is just a stupid black box. If you put in garbage, you get a garbage out of it. So the most important skill is how to learn to use AI machine learning tools. And I'm sure the previous speakers might have covered it. Swaminathan, he has given an incredible talk about how AI and data science plays a role, and what are the tools that you need to or that can come to your rescue. So it's to be very simple, Python. Python is the language that rules this field right now. So if you just learn how to use this black box, you can just fit anything in. It's not CFD, you can just fit in anything into it. And the most important thing that one should learn when practicing AI or machine learning is, when you get an output, does that make sense or not? Does that fit into if I do it in a brute force way? If I solve the equations on a paper, would the answer match with what the AI gave me? And that's very important that people sort of ignore these days, because if the AI spits you something out, people just assume that it is correct. So you need to check what the AI spits you out. And I had one question from Naren sir, that how is employment prospects for masters versus PhD at US right now? Could be one apprehension for students aspiring for. Yeah, so I keep getting this question of what are the employment prospectus if you pursue a master's. So master's has two different domains, and one should be very careful about that. Is, am I doing a research-oriented master's, or am I just doing a master's from a non-thesis background? Both have its own advantages and disadvantages. Thesis is something that you work with a professor on a research topic, publish your thesis in front of the committee, and that's how it's a research-oriented master's. On the non-thesis side, you just do the coursework. You take as many courses as you like, and just prepare yourself for the industry. So because no one cares where you did your master's in or which field it is from. It's not that limited in US. It's your coursework and your expertise that you can say to an employer. So nothing has prevented me to apply to a job and get an interview call in an investment bank. A PhD in chemical engineering is nonsensical if you see it from that perspective. So it's your coursework that defines you and not your degree. And that's the story with the master's. PhD is a whole different beast. PhD can be pursued right after your bachelor's or right after your master's. And so these are the two entry points into the PhD. In PhD, you spend 3 years or 4 years or 5 years, depending upon your mileage. But one needs to understand that how things will look like after 5 years, after you graduate. Do I have the skills that I can be employed? And that's very important to know. Once you have a PhD, yes, of course, you can always get the jobs if you lowball yourself. So yeah, if you apply for overqualified jobs, you'll definitely get the job. That's the lowest barrier to get a job with a PhD. But if you are very specific to your field, and it's quite easy to get a job. The job market in US is quite broad, and you can easily get a job if you know what you're doing. But I cannot speak of with other EU countries, but in Canada, things are slightly different. You have a very low pool of job market in Canada, even after you graduate. The job market is so low that finding a job, even if you're qualified, is quite hard. But in US, the story is quite different. If you are marketable enough and if you have skills enough, you can easily get a job in any closest possible domain. Any field that you join, you will have a learning curve. So the first 3 to 5 months will be new, irrespective of whether you join a chemical engineering field or whether you join an investment bank. So it will be new to you. It's just the skills that you acquired in your coursework that will define you or prepare you for the job. That's it. Be your two best advice for the current students. What do you think you have? I'm short on time, so I can answer a few questions, and I have some agenda that I just want to cover.
Yeah, you can, after this question, you can go ahead with whatever points you have prepared also. so that
Sure.
that's
Okay.
also covered. Yeah, no issues.
Yeah.
Yeah.
So yeah, when I missed at
Or
what
you
I
can
missed,
take this at the end. It's okay.
I'll just answer this question. It's right over here. So what I missed during my undergrad is doing a research-oriented work. I mean, people might have been enforcing you, or the way that our curriculum is set up is you do in-plant trainings. I mean, I too did in-plant trainings at Billai Steel Plant, NTPC, Korba, uh, in my second year, third year summers, and my final year, I just went to NCL. So these in-plant trainings were to understand, were to connect the dots between what you have learned and what happens in the industry. I mean, you will not, frankly speaking, you will not learn anything from these in-plant trainings. It's just that you will know what is happening in the industry and where you as a chemical engineer would fit into the big picture. So that'll just give you a reality check. If my skills and what am I doing is really relevant to the industry, or even if it is relevant to this specific industry or not. When I went for the first in-plant training at Billai Steel Plant, it was filled with mechanical engineers, electrical engineers, and there was a very minimal scope for a chemical engineer. And that's how I came to know that chemical engineering has a very, or the job openings or the people who work there has a very minimal footprint for the chemical engineering. And after that, I went to a national thermal power plant in Korba, Chhattisgarh. And that's where I came to know that chemical engineering plays quite a bit of footprint, and that too, not in the power generation or the turbines, but in wastewater treatment. So that's where I worked for RO plant water treatment, because these turbines need a really good quality of water. So I understood the role of chemical engineer and how, and that really, and it's a eureka moment when you see something happening and when you realize that it's from the textbooks that is happening. So yeah, that was one of the moments. And after that, I went to ONGC in Tamil Nadu, Karaikal, I think, and that's where is just a full-blown chemical engineering operation. And yeah, so even though I did all these in-plant trainings, which were enforced, or which was just seen as a practice to connect with the reality, my goal was all research oriented. If people are inclined with doing research or something, I had very minimal options or guidance of how do you do a research sort of project. I'm pretty sure that people are now visiting NCL, IITs, IISc to do a research-oriented work. So I didn't have that option back then. So if you are inclined towards research, align your goals accordingly. If you are inclined towards a career in industry, incline your goals in that way, doing in-plant trainings, and just don't mix. And the skills that you learn or come across in in-plant training does not apply to research, and there is no overlap at all. So if you have time and if you are quite sure enough what you want to do, like, try to segregate. If you want a career in industry, or if you want to know what is happening in industry, do an in-plant training. Or if you are inclined to do a research oriented or experiments, or just do a lab work sort of thing, get a research oriented internships. So that was the point that I was missing back then when I was doing my bachelor's. So the best advice, I'm really not qualified to advise anything, but my 2 cents here is project what will be happening down the line. So yes, you will be doing a lot of traditional work in your coursework, but my suggestion here is, in any project or any final year project work that you will be picking up, try to add 5 to 10% of some X factor of your interest. You might be doing some experimental work that the department wants you to do, in most cases, I hope, and some part of the computational work if you're doing, but always involve 5 to 10% of something X factor that you can involve. I'll define what that X factor is in a moment. You might be following certain steps. You would be choosing a topic, working on your thesis, on your project work, doing the experiments or computational work, just the regular job. What is something totally different that you're doing? I mean, how does your thesis, or how are you distinguishing yourself from the others? That's the question just you need to ask yourself. You don't need to reinvent the title and do something that will be published or get a Nobel Prize or solving one of the pressing problems in the society. It's as simple as, should I publish my should I write my report in Word, or should I use LaTeX? LaTeX is something is a documentation software. It's a skill that is really admired in research, and if you can develop that skill and write your report in LaTeX, that's just that 5% of or 10% of X factor that you have put of your own interest into the project. That's one. And second is, people have been classified as experimental projects and computation projects, but give it a thought that, can I do a hybrid project where you can have both experiments and computations coexist? This might be something new, but it's something that you need to be prepared what will be happening in the future, but not what is happening right now. I mean, the skills that you are learning right now might be irrelevant as soon as you graduate. It's a fact, and it happens in every discipline. It's just an evolving world. So always think about, I'm not saying that you need to study and just practice everything that you don't know, and you just get to know what is happening in other fields. And that's how you will be prepared of what will be happening in the next 5 years or so. After your graduation or throughout your bachelor's, you might enter into a chemical engineering field or not. You might be picking up a career in IT or not. You might be doing a higher education or an MBA. And these skills might not be completely transferable, but just get to know that how can you be creative, right? So, and what sets me apart from the rest of the pool? And that's what you need to develop. So ask yourself that, what will be the best thing, or what will be the hot topic after 5 years that I can think of right now? And you don't, and people talk about AI, machine learning. You don't have to do that in your final thesis project, but read something and connect that AI or machine, write a single sentence that AI and machine learning helps to solve this problem. If I had time, or if I had time to solve this problem. And if you are clear enough how AI and machine learning can answer that, you have done that 5 to 10% of X factor that you need to put in your report. So yeah, my 2 cents is just do that 5 to 10% of extra that you are not taught as a part of our curriculum. And that can be and that freedom, you can only get it from your project work. Because there is no exam or a curriculum that defines you to do it. So that's the only spot, or that's the only freedom that you will see to have, that you can put a complete your interest into the project. Well, I'll pause here for a moment, and I can just take any random
Yeah, but you had some other thing also, right, which you want to cover. So I think it's better you just cover up that. I think your phone is muted.
I'm sorry. Yeah. So I keep getting questions about, is my chemical engineering skills relevant to other fields, and how do I fit into the job market? Irrespective of which country you are in, even in India or US or any other country, how does your skills relevant? If we as chemical engineers look at what we did, the first thing that comes to your mind is unit operations processes, CRE, heat and mass transfers. Yeah, these are really core subjects of chemical engineering, but I would suggest that you also pay attention to electives outside your department. Uh, like when you do engineering math, that just seems no-brainer to you, solving some Rangekuta methods, uh, stuff like that. But if you ask Naren sir, how does that fit into a CFD, he can just give you an example right away. Uh, so you have a practicing resident CFD expert of how the math that is being taught applies to a real field. So whenever you feel that what's the real application of the subject that you're learning, just ask questions. That's the first step and the only step that you need to take. So like you can take like space biology or whatever electives, organization behavior. uh, I don't seem to recollect any courses that I did, but any course that you did, and if that seems a no-brainer to you, and if it seems monotonous, like you do something and you write an exam and then you just forget it, just ask yourself what that has to do in a real practical world, and just ask the question to anyone. And I'm sure there are many people out there who can answer that question, or or at least they can guide you to answer that question. Yeah, I'll stop right here and I'll take any questions you have.
Yeah. So this is the pointer that you wanted to add.
Yeah, that's the only one. Yeah.
Okay. Yeah. So that's fantastic. So it's good. Like we had almost 1 hour 15 minutes of very good interaction. I'll just wait for if there are any questions. Somebody wants to unmute and ask. You can feel free. As Abhishek's. Yaar is it?
Sir, I'm Shrikar, sir.
Shrikar, yeah. Telugu or English or Hindi? What you want to pick?
Yeah, English. I mean, there are a lot of audience. So,
Right.
and actually, I had a doubt that. So, I'm currently pursuing a master's in chemical engineering at IIT Kharagpur. I'm taking chemical engineering at IIT Kharagpur. And what I realized is I have interest in two topics, which is one of them is process intensification and other is sustainable technologies. So, it includes, I mean, also CO2 sequestration and stuff. And these two things are very, very low in demand, and these two things will get a very low support in India. The funding is zero. It is only at the lab scale. There's no point of going from lab scale to industry. I mean, I've talked to the professors and they're like, no, that's all funding we have. Sorry. So, I mean, my query was now if I want to pursue anything future in, if I want to pursue my career in this stuff, which is kind of like, is not completely research nor completely industry based. It's kind of a transition between the research to industry based. So, is it, should I do masters again, MS plus PhD again in US, or I'm in a crossroad there. So you please.
Yeah, sure. I understand your question. So process intensification and sustainability research, I mean, these are two different areas. Process intensification is almost stagnant to my knowledge. Back in 2012, when I graduated, process intensification was a thing in NCL, which was funded. It was called Magic Project, if I'm right, Naren sir. And it was about, like, if you just think about in common sense terms, process intensification is almost stagnant. Everyone knows what to do in the industry. They are doing it their best. Otherwise, they wouldn't have run the industry. They have optimized the plant operations to a maximum extent possible. So digging further into process intensification has a very less scope. And that's the reason why you see that the funding from the government or from the industry is quite limited, because no one wants to allocate money. I mean, everyone wants to allocate money in emerging technologies, right? So that's one thing. Sustainability engineering is a huge field. It's just not limited to chemical engineering, chemistry, material sciences, AI, machine learning. So your question is, I'm already pursuing an MTech. If I had to pursue a master's, or if I had to pursue a PhD, do I have to go through a master's again? Is that your question?
It's kind of like the job perspective of such industries is more prominent in US. So if I want to get a job there, and should I do my master's again, or should I be doing a PhD?
Okay. Yeah. Let me just answer this question, and it's a fact that I should be stating. It is incredibly hard to get a job in a chemical engineering industry in US. Even though you have like 100x, 200x more chemical engineering industries in US and compared to India, getting a job is incredibly hard. When I say chemical engineering industry, I'm talking about traditional industry, where you do a paper, petroleum, textiles, water purification, all these industries. It's very hard for an outsider. When I say outsider, it's an international student to get a job in core industry, because you don't have practice. It's just not about unit operations and your knowledge. It's about the practice that is being adopted in the US industry that is different. So you are certainly not the candidate that they would be looking for. And the job market is really, really low. So, and it has been like that for many years, from past decade. So I'm not saying to discourage anyone. It's just the fact that even though there are like tons of industries, there are very minimal job openings for an international student after you graduate. That's one. Second, if your engineering or if your specialization is process intensification, my 2 cents is, how do you market that to get a job? Or how do you pursue yourself a career, extend that process intensification? So look for something that can add an addition to what you have done. So think about, how do you add the hot topics these days, the AI, machine learning, into process intensification? How do you add automation into process intensification? Or how do you do process intensification for emerging materials? You might be handling very traditional chemical these days, but if you add fine and specialty chemicals, how do you design something really unique, or really something very economical? So just move away from traditional process intensification and do interdisciplinary stuff. I'm not asking you to reinvent something or reinvent the wheel. Just add something to it with emerging technologies that will make you marketable. Does it answer your question?
Yes, Anaya. Thank you.
Yeah. So anyone else who would like to ask any query? Okay. Okay. So if there are no more queries, I think it's a good time we can close this session. I'll just ask maybe some student who wants to give a final summing word, conclude. Somebody wants to do that? Or hello? Yeah, I think people are.
Yeah, it's almost time.
It's almost time.
Um, so may I add something?
Yeah.
Am I audible enough?
Yes.
Yeah. Okay. Thank you, Abhishek, for the talk. When I joined, I'm currently working with a startup that makes fuel cells, hydrogen-powered ones. So when I joined this place, I was wondering what I would do. I mean, where I can add being a chemical engineer. So when we started modeling fuel cells, we had assumed that each cell would be a CSCR, and the moment I heard CSCR and I was on. So it felt really good to add something to a place where you thought that you would be of no use actually. So I had such similar moments that I could totally relate to you because of such little moments that I had when I joined working with fuel cells. Yeah.
Yeah,
So
that's a good
it was
point.
it was a great talk.
Yeah, thank you for that.
Thank you for that. And
Yeah.
I see a echo.
Uh, is it okay now?
Yes. Oh no, I see. I think you need to unmute yourself. Sorry,
Yeah,
mute
one
yourself.
second.
Uh, uh, well, yeah, Shweta, I think, yeah, I too did my first paper in the fuel cells. As Naren sir has mentioned that it's one of these disciplines that you will, so people when start looking for jobs, they look into traditional industry like petroleum, textiles, and stuff like that. But there is a huge world out there where you are employable with the skills that you have. So apply in the places that no one will actually find you. So you already have the skills. So just apply wherever you find that you can do a good job, or at least you can get an entry and do a good job. So yeah, as Shweta has found herself in the fuel cells in it's not a traditional chemical engineering market in India, but it's mostly occupied by electrical engineers and mechanical people, chemistry folks, but a very minimal footprint for the chemical engineers. So yeah, it's good to know that eureka moments where you can connect the dots in different fields.
Yeah, thank you.
So
Sir.
with that, I think, yeah, Acha Kalaivanan, yeah, go ahead.
Hi, Abhisek, brother. My name is Kalai. I'm like right now in 4th year. Like we have been asked to decide on our final project. So for the past 6 months, while I was in home, I have been like seeing many news or hearing more about hydrogen fuel cells and those kind of things, and I got some interest in it, and I've been researching a lot in it. I've been studying how those goes, how they store, what are the drawbacks, what are the problems, what needs to get a breakthrough so that we proceed. And right now in India, we don't have a scope, and it's been predicted by many people that it has like around like more than $1 trillion economy in the globe. So I kind of feel like, what do you say? Like you just now said that you were also into fuel cells. Like, can you suggest what to do next?
That's a broad question to answer. Well, you have done enough work to actually write a perspective review article yourself of the introduction process and challenges involved. So, I mean, I see that you have your in the audience, Shweta. She is working on the fuel cell side of things in India. She is the best. She can just give you the best ground report what is happening in India. To answer your question about fuel cells, yes, fuel cells is an emerging market. It's an emerging technology. It's one of the key emerging technologies. You can see a lot of research work being done. It's almost getting into a stagnant field. I mean, many previous speakers, Nitish, he worked on catalysis, fuel cells part, who's 2013 or 14 graduate.
13. You're junior,
13.
1 year junior. Yeah.
Oh yeah. So yeah, we had an overlapping stay at. He was at Carnegie Mellon, I was at University of Pittsburgh, and I took some courses with his advisor. So yeah, fuel cells in the research domain is pretty stagnant, but there is a very minimal success in terms of commercializing those technologies. So yeah, there are. I wouldn't say there are many startups at all that is driving this. So I would say try to find a startup. If you have enough skill sets and interest to make an impact on the fuel cells, try to look for startups. You might not find that easily. Startups are less known anyway. So try to find startups that are actually working on fuel cells. You might not be successful there, and the startup might not be successful there, but you will get the most important experience of how you can fail or how you can make it succeed. in the fuel cells that can prepare you for the next year. No one, it's very hard to get a success right away into a new field. You fail there, and that's your experience that will make you employable. Even if you fail, the failure is your qualification that gets into your next job. So try to find if there are any startups. There are many think tanks who work on fuel cells in India. Try to find information, as much information as that, who are working on fuel cells. It is not the traditional job market that you see from what others are doing. But if you're really interested and if you have enough knowledge about fuel cells, try to find that, and I'm sure you will have a good amount of success there. Does that answer your question?
Thank you, senior. Sir, 1 minute, sir, please. Okay. So, what you said, the last point you said is like, thank you for that. And that was what I was mainly thinking about. But I'm currently worried about right now in the hydrogen field, which you are mentioning that it is becoming stagnant. It was stagnant from 1940 to till now. And in this decade, there was a hype for it, for renewable energy and non-zero pollutants or emission. So it became famous. I'm kind of worried that if I join a startup, right now a current breakthrough is needed in the field of storage of hydrogen. There needs to be much research. Like, I can't say that a computed field research is possible in that, like, in a material world. So I'm worried about it, that whether should I proceed in a material research oriented based path or in a startup, which you said right now. I'm just worried about it.
Yeah. Okay. So, all right. If I understand your question, I might have misspoke myself when I say this. The field is stagnant. The field is stagnant in terms of it's just not the hydrogen based fuel cells. Just don't limit yourself to hydrogen based fuel cells. That's the first point I would like to make. There are like other natures of fuel cells, solid state batteries, lithium batteries, and all that, which does the same job as hydrogen based fuel cells. Yeah, of course. At this point of career, just keep your horizons open. The concepts that you learn with the hydrogen based fuel cells applies to any other. So just keep that open and see where the opportunity comes from. Second is, the field is stagnant in terms of research. I mean, when you said hydrogen storage research, that's the research that my advisor has done in 90s in metal hydrides and stuff like that. Significant amount of computational work and experiments were already done. People have already identified a significant low-cost materials. The barrier is commercializing these technologies. That's the barrier. It's not the materials or the research that is lacking. And that's what I meant by the field is stagnant. So the bottleneck is commercializing these technologies, and the answer lies in the startups, because they are actually trying to solve this commercialization problem. So, well, the computations and experimental work is already being done, to my knowledge. Like it's the practical engineering problems that one needs to tackle to commercialize these technologies. So my 2 cents is, I mean, you know why the hydrogen-based fuel cells are a hot topic these days. It's because of the vehicular industry. There are I think Toyota has the hydrogen fuel cell car, and there are many. IIT BHU has a hydrogen fuel cell auto, I think, a 3-wheeler, back in 2014 or so. So it's about commercializing these technologies. So that's where the bottleneck is, and that's where majority of the think tanks and the startups are trying to solve a problem. It's not, I wouldn't say there is a huge interest in research or experiments that needs to be conducted to the knowledge I'm aware of.
Yeah. So that's, yeah. Right. Anyone else? Okay. So I think it's a long Sunday morning for Abhishek to gear up the students for the next week. Thanks, Abhishek, for coming forward to share your thoughts. It was a very nice extempore, and I'm very happy that with this we conclude the 2020 series of talks. This is actually the 24th talk, so that means we are at the rate of 2 talks per month. I'm very happy that it is at this rate, and I'm sure that we will keep up this as a one sustained activity. So, like Shrikar said, this should be at least sustainable as part of the ISHE or the student chapter of the schema. And to all the juniors, you should thank Abhishek and his batch, his classmates, for they started actually the ISHE student chapter because they wanted a kind of recognition within the university. They just want to know that yes, there is also a chemical engineering department,
Right.
and that should be known.
That was my motivation when I took all those applications, got it signed from Kumaresan sir, and then mailed them to Annamala University, because I think that's
Yeah, we still attached to Annamalai.
okay. Yeah, that was a major goal when I asked people to sign the applications, ask them the fee for the application, because when you ask for a fee, it's not that easy to get the fee.
Yeah.
So,
and one more, this I reserved at the end because it will be nice to conclude. Now there are many people. I mean, like in the final years, I won't say this is a gray area, but I would rather now say of Abhishek, which is very distinctly different of his trait and also of his batch at large. Abhishek and a group of his own friends, they used to come and talk when they are in the final year. They used to come and talk to the second year and third year what they should do, what they should guide. So there will be like some sessions, whether 10 people attend or 20 people attend, but it was never only they were talking, there were always people were ready. So they used to arrange, and mind you, this was the pre-ISCHE era, when there was no body like this, there was nothing like that. And how I came to know, it's a very nice thing, because I was not there at that time when Abhishek was doing all this thing in his 6th semester and something. I was not at all there. I joined when he was already in the 7th semester, August. His juniors told me. So I asked how you know all this. His juniors told me. So Abhishek and his other friends, goodwill friends, I mean, their class batch was like a collection of many abilities put together. Right. So Abhishek was like a kind of a think tank for academics. So he used to come and talk to his fellow juniors that you can do projects here, you can do industrial internship here, or something like that. I mean, wherever they went, afterwards they used to arrange a talk, share this. This is something very strange, and eventually this culminated to creation of ISHE, and they had the very first event of Prakriya. And I would again fondly recollect every time when a 2012 graduate batch comes and talk that we had cranes and all to put the decorative whatever items. I mean, near the Krishna canteen, they took a huge crane to put a very long handcrafted posters. And that was all done by his classmates and friends only. Yeah, Abhishek. Yeah, you had something to tell?
yeah, it back in the time we didn't have an official body when we were just doing sort of these things. There was a huge disconnect between each and every year. There was no interaction between the juniors or the seniors. That had been the custom or the culture for several years, but we did off the record most of these things with the juniors or the seniors. That it was mostly after 5 during the weekends that we used to sit and chat about. It was mostly irregular, informal get-togethers that we just sit and chat. That's it. That's all we did, and that's how Kumaresan sir told me about ISCHE student chapter. It was delayed a semester. I was lazy enough to do that, but I got the applications to get signed. It was a lot of manual work, but I'm very, I'm really fortunate that Naren sir joined in August 11, after the things started to change and catch up, there was introduction of computation oriented teaching, in-plant trainings, research internships, exposure to what is happening to the outside world. This is what you need the mentoring for. And we didn't have such sort of mentoring back in those days. So I'm really fortunate that you guys have it, and envious as well that you have Naren sir during your semester. And I just don't want to hang you guys out for long, but I would just wish everyone the best, and happy Christmas and happy holidays.
Yeah. So thanks to all of you, and a very happy New Year. And 2021, we will again meet with the next year series of Google Meet. Thanks, Abhishek. Thank you.
Thank you.